Hello folks, and welcome to this lesson on electrolytic cells. By the end of this lesson, you should be able to explain how current is conducted in an electrolytic cell and deduce the products of electrolysis using standard electrode potentials. Now let's take a look at all of this by looking at what electrolysis is first. So if you take the word itself, you have electro and lysis. Electro refers to electricity and lysis refers to breaking. You probably see that suffix of lysis quite a bit in biology. So you have things like cytolysis and so on and so forth, but that's where the word comes from. This idea of breaking something using electricity is not going to happen exactly in the way that you expect in every single electrolytic cell, but it is more obvious in some of them. Now, what's different between electrolysis and everything else with redox reactions that we've seen so far in the lessons is that you're actually going to be taking electrical energy and changing it into chemical energy. So the chemistry part of it, the reaction, doesn't happen on its own. You have to put in electrical energy to make that reaction happen. And as a result, you're going to need some sort of external source of electricity, and you're also going to have an electrolyte in there somewhere. Your electrolytic cell is generically going to have this sort of a format. So you have your electrolyte, you have your electrodes, and then you have your external source of electricity. Now, when you're drawing in your external source of electricity, the direction that you're drawing it is going to matter if you have to draw an annotated version of an electrolytic cell. Another big difference between this and a voltaic cell is there's no physical barrier blocking the half reactions between the two half reactions. The reason is because you don't need one. These reactions aren't going to happen spontaneously, so you can leave everything as it is, and it's not actually going to start doing anything until you actually put in that source of energy. Now, if we're going to label everything, we are still going to continue, or I am still going to continue to have the anode on the left and the cathode on the right. But a difference between this and your voltaic cells is that we've changed our symbols. Now, the fact that we have oxidation happening at the anode and reduction happening at the cathode is going to stay the same, but the symbols have changed. Now, if oxidation is still happening on this side, your electrons are still going to be released from this side, and your electrons are going to continue to being used up on this side. However, for this we have to go back a few definitions, back for a long time, because remember, in a circuit, the electrons flow from the negative side of the cell to the positive side of the cell. So that's the negative side of your battery to the positive side of your battery. Now in this particular case, the negative side is this side, and yes, the electron flow is going to happen in this direction. But this is a positive end of that battery where electrons go towards, and this is a negative end of the battery. And so that's why these symbols have flipped. The reason why it's the other way around in a voltaic cell is because this end is a negative end of the battery itself, because this is the battery, not this. This part is the battery in your voltaic cell. So electrons are being released from this side, go to the other side, so it's going from negative side to positive side when this is the battery. But it's not the battery in an electrolytic cell. So this is going to be the general idea of what an electrolytic cell is going to look like. The details in terms of the half reactions are going to depend on what you put in it. So there are plenty of things that you can put in electrolytic cells, and we're going to divide them into three categories of things that you might need to consider when you're sketching out and figuring out what's going on in an electrolytic cell. The first type is you take your ionic compound, you melt it down into its so that the ions are free flowing, and then you stick some inert electrodes in there. The second type is when you take your ionic compound and you dissolve it into water, you have an aqueous solution, and then you stick some inert electrodes in there. And then the third type is take it, dissolve it into water, and then you use non-inert electrodes. So the electrodes themselves might react. So first off, let's look at the molten one. So first we want to draw our general structure of everything. And now let's fill in the details. So from here, we know that at our anode, we're going to have our oxidation reaction happening. And the possibilities here is you have your sodium ions and you have your chlorine ions because we've taken molten sodium chloride. So your choices are between the two. And honestly, the only thing that's going to happen in terms of what we have here is your chlorine ions are going to become chlorine. And as a result, you're going to have the release of an electron. Now, in the same sort of idea, the only thing that's really going to happen here is that your sodium ions are going to become sodium. And in the process, they are going to take in an electron. And then finish off with your half reactions and then your overall reaction. Do note that most of these things are going to be in liquid form rather than your usual solid, because to melt sodium chloride, the temperature is going to have to be pretty high. Now things are going to get a little bit more complicated once you start putting things in water, because yes, it is going to be easier to actually do in terms of producing this electrolytic cell, because you don't have to heat it up to ridiculous temperatures. But at the same time, you're now introducing more possible half reactions. And the thing is that at the end of the day, the reaction that actually happens is going to be the one with the highest E negative value for the entire cell. So first off, let's list all the possible half reactions that can happen with this situation. So let's take all the possible reactions that you can get from your list of standard reduction potentials, and then I'm going to be highlighting what we actually have so we know which direction we should be looking at. As a reminder, what do I mean by that? Well, the thing is that in this situation, we only have sodium ions, we do not have sodium metal. So that means when we're looking at this half reaction, it can't happen either way. You can't have the sodium becoming sodium ions because we have no solid sodium. So when we are considering, can we look at this reaction? Is this a viable half reaction that might happen? We can only look at it in the forward direction where we are taking the sodium ions and reducing them. And same thing down here. Yes, the only thing we have in this situation at the proper concentrations and such is your water. So if we're looking at this particular half reaction, we're always going to be looking at it going the other way. We're looking at it in the oxidation reaction because we don't have these things to reduce. Now, since we're going to be looking at these two as the oxidation reactions, when we're looking at the overall cell reactions, the E0 values that we're actually going to be using when calculating the E0 of the entire cell is going to be these numbers. So at the end of the day, for our overall cell reaction, we are looking for the one that will give the highest overall cell reaction. So we just have a whole bunch of negative numbers in here, so we want to have the least negative number. And the combination of reduction reaction and oxidation reaction that will give you this are these. Now, this particular setup has a little bit of an exception to it. And the reason that you have this little bit of an exception is because these two values are so close to each other. Now remember the fact that all of these standard reduction potentials are based on the fact that you have a 1 molar solution for anything that is in aqueous form. But if you change the concentrations, these E0 values also change. And so because of that, because of the fact that these are so similar to each other, if you change the concentration of your chlorine, you can actually have it so that this half reaction is more favorable in those situations. So whenever you see chlorine ions in an aqueous solution and you're doing an electrolytic cell, take care of the concentration of the chlorine ions. If the chlorine ions are high in concentration, then this is actually the half reaction that will happen at your anode. And then if your chlorine ion concentrations are low, this is the one that will happen. Hello folks, apologies for this awkward insertion. In my original video, I said that there were two situations where you had to be careful about the whole concentration thing. There isn't. It's just the one, and it's the one with chlorine ions. So yeah. Now for how this all works in terms of, well, why higher, why lower, this comes down to the equilibrium unit. If you've already done it, then see if you can figure out why this works out that way. If you haven't done the equilibrium unit yet, then wait for that. And then for our third situation, we have the aqueous solution with the electrodes that can react. So, more half reactions to look at. Yay! So first off, let's list all those half reactions out. And then let's highlight the species we actually have. For the species where we can only do oxidation, let's flip some of those numbers. And then look at our possible half reactions with our reduction reactions. This one will give us the least negative E0 value for our overall cell. And then in terms of our oxidation reaction, this half reaction is going to give us the least negative E0 value for our overall cell potential. And so the two half reactions that are going to happen in this electrolytic cell are these two. And so therefore, when you're drawing and labeling an electrolytic cell where this is going with this particular situation, your half reactions that you're going to list are going to be these two. That's the end of this lesson. I'll see you next time.